Thank you for that introduction. Hello, everyone, and welcome to my presentation tonight entitled Durable Microservices with Wasm. Very excited to be here tonight, and I know that you are all tired, so I'm going to try to get through this as fast as I can. All right, so what I'm going to talk about tonight is a simple API, and I'm going to motivate the use case for the technology that I work on my day job, which is a new open source project called Golem. We're going to be hearing a lot about Golem. And then after I motivate the reason why that technology exists, I'm going to take a look at how that technology can be used to solve problems that many of us developers have faced numerous times over the course of our career. And then finally, I'm going to give you a sneak peek into where I think this type of technology is heading, especially in the Wasm ecosystem. Just a simple API. All right, so it is 5:15, and I know you're very tired. You've been here for 2 days. You've attended dozens and dozens of talks. You're exhausted. You want to get your weekend on. You want to do whatever fun stuff there is to do in Barcelona. I know there's a ton of great stuff to do. But then your phone starts ringing. Ring, ring, ring. Who could it be? I wonder. And so you answer your phone, and oh no, it's your pointy-haired boss. And he has a tiny little assignment that he wants you to do before you kick off your great weekend in Barcelona. What is it? Well, he just wants you to add a new checkout API for the mobile app your company is working on, right? Just make sure you do that before you enjoy your weekend in Barcelona. So he leaves you, and you go into your cubicle to think about your life choices. And after some amounts of reflection, you're like, this isn't too bad, right? This is not too challenging. This is something I can handle. I'm going to get done in plenty of time to enjoy the weekend. After all, checkout processes are not that hard. Right? There's only a few steps involved in checking out a user from some sort of online shopping store. So what do? Well, you write your checkout function in TypeScript, and the first thing you do is check and reserve inventory to make sure that the warehouse can actually satisfy the order. Why do you do that check? Because you're about to charge the user's credit card, and you don't want to charge them unless you actually have that many items in the warehouse for delivery. So you make that check, and then you go on to charge the user's credit card. And that way, they'll only be charged if the warehouse can actually deliver on the order. But you're not done there. You still have a few steps left. After you've charged the user's order and the inventory is reserved in the warehouse, you now know that this order will be fulfilled. Barring something catastrophic, the user is going to get their stuff. So you need to call into UPS or DHL or whatever shipping company of your choice, and you need to generate a shipping label and a tracking number. And you specify the weight of the goods and the dimensions of the box, whatever. You specify all that, and you get back your shipping details. After you have your shipping details, you can now dispatch the order to the warehouse because you have the label, you have the tracking number, you have the order. The customer has already paid for their order, so now it's time to get that thing in motion. And then finally, after all those steps have been completed, you send the user a confirmation email saying, here's your order, here's the tracking number, good luck. See your stuff in a few days, hopefully. All right, well, that wasn't so bad, right? An hour later, come on, it wouldn't take us that long to write that code. It's not that much code. It fit on one slide. We pushed that code to Amazon, right? And we're about ready to celebrate. Here we come, big weekend. But then a little voice in the back of your head starts talking. And it's saying, are you sure you've analyzed all 4 million possibilities? And so you begin thinking through different failure scenarios. That little voice, by the way, it's a distributed systems engineer. And he sits in the back of your head, reminding you of all the terrible things you're about to do. You sit and you think, and you immediately come up with a failure scenario that's pretty bad. This failure scenario is you reserve inventory at the warehouse, and then something happens to that running program. The server dies, Kubernetes kills it, developer pushes a new update, something happens right then, before the next line of code is ever executed. And so you have the situation where the user clicks the buy button and the inventory is reserved, but nothing else happens after that fact. That's it. And no payment is ever processed, and those items in the warehouse will just sit there reserved. Okay, that's a problem. That's a discrepancy between the real world in which the user hasn't actually ordered anything because that process didn't complete, and then the virtual world in which we're still holding on to some items and we're not releasing them for other people to buy. That's bad, but it actually gets worse. Your brain starts thinking, and you immediately run across a second failure scenario in which the payment is processed. You actually charge the user's credit card. So you do the first step, and then you do the second step, and then something bad happens. The server runs out of memory. The instance just goes down. It gets degraded and goes down. And so now you're in the situation where the user was charged, the items are reserved, but nothing is ever going to happen. Those items are always going to be in the warehouse. Everything downstream of those first two steps is never going to execute. That's a major problem because the customer is going to be pissed off that they paid money for something that is never going to arrive. All right, so let's take a step back and figure this out. How many failure scenarios are there in total? Any guesses? Can we say? No guesses. I can tell you what the answer is not. It's not 5. And you might think, oh, well, in any sequence of n steps, we can fail in between the steps, and therefore there's n-1 failure scenarios. Wrong. Why? Because every function we're calling consists of another m steps, let's say. And those steps may or may not be atomic, and some of them may or may not involve concurrency. So even a small program like this could have hundreds, thousands, or tens of thousands of different failure scenarios. This is why distributed systems engineering is really hard. And so you walk away from that simple code that you wrote, and you're like, what do? I don't know what to do. I don't even know if I'm going to be playing this weekend. I might have to work in the office both days. And that's when you call your friend. You know the guy, super nerdy guy who delights in reading academic papers. This is the distributed systems engineer. Everyone knows at least one. And you ask him, hey, how do I solve this problem? And he pulls out this equation here. Nice, simple equation, he says. This will give you everything you need. This just says in any distributed system, it's possible to realize the current state of your application as the semi-groupal composition of a bunch of reified patches representing state changes. In English, chop up your application into little tiny bits called events and construct the current state of your application through a fold over those events. So in this way of programming, which is probably the dominant way we build highly reliable, highly scalable systems today, the huge advantage is that we can take every discrete packet of information that results in a change in the running state of our application. These things are called events. And we can store it inside a fault-tolerant, redundant, cross-data center replicated queue or NoSQL database or whatever else we want. And so if something bad happens to any piece of infrastructure, a node or the server or request handler, doesn't matter, we can always reconstruct the running state of our application and we can resume processing. So many of the biggest, most reliable systems out there are built using some variation of this pattern called event sourcing. The bad thing is that simple code we wrote that we did in 10 minutes, that's not going to work anymore. No, we're going to need to take a sledgehammer to that code. And step number one is we actually have to extract a bunch of events. And events represent tiny little steps in the progress that our application is making. How many do you extract? Well, that requires some judgment. Too few, and you're going to run into reliability problems. Too much, and you're going to run into maintenance problems. And once you extract those events, by the way, and then deal with the infrastructure involved in persisting them and serializing them and everything else, then comes the fun part. You need to take what was a very simple, straightforward, imperative process representing checkout that probably just follows the structure of the user story, right? There's nothing fancy going on there. And you need to transform that into what's called a finite state machine. And state machines, this is my poor man's attempt at a state machine diagram because I couldn't figure out how to draw some stuff in Google Drawing. State machines provide you with a deterministic way of reconstructing the application state from that series of discrete events. And then you write the state machine. I can't fit that on one page. I can't fit that on 10 slides. That's too big. There's too much code here. But this is a little snippet of the rewrite that refactors that checkout into state machine style. And then in addition to this, you need all the serialization, the deserialization code, the code that talks to Cassandra or Kafka. Probably you need some sort of schema registry to maintain long-term schemas. Probably you need to do validation on the data you're reading in case of mismatches. There's all sorts of stuff that you have to write in order to make this work and scale. 2 months later, you've given up on that weekend. It didn't happen. I'm sorry. And you've ended up reconstructing modern application architecture. It's a mess. And yeah, these systems are highly reliable, and they're very scalable, and they can be as stateful as you want, but they are a pain to build, and they're a pain to maintain, and they don't allow businesses to go fast, and they're not fun to work on. All right, well, we made a mistake. We need to rewind the clock. We need to go back in time. Really, we need to go back 30 years because that's when we started making these mistakes. But for our purposes, we're just going to go back to that point when we made the decision to deploy this on Amazon. And that brings me to Golem. So Golem is a new open source project that is trying to revolutionize the way you build highly reliable backends. So if you're trying to build a microservice or an API or some sort of web service and you want that to be extremely reliable, like that checkout example, then Golem is trying to be the open source platform you use for building and deploying that backend. Its claim to fame is transparent high reliability, which we'll see here in a second. You go back to that simple-looking code that you wrote in 10 minutes, and you're like, this is the code that I really want to use. So you do. And you write this simple, impossibly simple-looking code that you and I both know can't possibly work. Right? There's no way code this simple can actually work and be reliable. Not on today's cloud. It's too unreliable. But this time, instead of pushing to AWS, you push to Golem. And something happens. That little voice in the back of your head, silent. Right? He's not talking about failure scenarios anymore because there are none. There are no more failure scenarios. All the failure scenarios that I mentioned before, gone. Poof. In fact, that program of yours that is now running on Golem can survive hardware failures. CPU catches fire, doesn't matter. That program will be relocated to a new node, and its state will be reconstructed, and it will continue from the very line of code that it left off on, without any intervention or supervision. And from your point of view, it's as if nothing happened. There's some sort of server error, doesn't matter. There's a catastrophic bug that brings down the server, nope, it's not going to affect your program. The server's restarted, or maybe a developer issues a new version of the application. They change some code in there, and that rolls out a new version of the application. Doesn't affect your running code. Your code continues to execute in a fault-tolerant, update-tolerant, and even flaky-tolerant way, giving you instant and transparent high reliability. And you didn't have to do anything except push the big deploy button. Yeah, our weekend is back on. We're going to have a good time. So what's the secret behind this? It sounds, when you describe it to people like that, they're like, what's the catch? This sounds too good to be true. What's going on? And I wish I could claim credit for that, honestly, but I can't. The secret sauce at the heart of Golem is none other than WebAssembly. WebAssembly gives us a deterministic virtual machine that has a capability-based security model that ensures that a WebAssembly program can only do exactly what you allow it to do. WebAssembly programs don't have native capabilities. Every capability they have is passed into it from the outside world, which means the outside world that's running your WebAssembly program has 100% control over everything that happens. And then in this day and age, we have WASI, which is a sort of foundational system call-like interface that allows us to build all of the other stuff that's in our standard libraries and frameworks and third-party libraries. And WebAssembly gives us cross-language support and cross-platform support for free. If you wanted to think about solving this problem for machine code, you wouldn't even know where to begin, right? Machine code, if you wanted to execute that in some sort of magical way that can survive failures, you now need to deal with the fact that machine code is not deterministic. It's open-ended. It can do anything that it wants, right? It can install interrupts. It can execute things which are not code, right? There's a billion different things it can do to escape its sandbox. And then beyond that, which machine code are you going to choose? There's dozens of CPUs out there, CPU architectures, and you can't support them all, right? The task of building transparent, high reliability on machine code is just too monumentous to even contemplate. But the WebAssembly VM, small, precise, deterministic specification that makes all the right decisions from the point of view of security, that is something that we take advantage of. This is how every WebAssembly program in the world looks. You got your user logic up there at the top. And then underneath there, you have all the frameworks and libraries that you're using. And then underneath there, those frameworks and libraries, maybe they all go down to your programming language's standard library. But in any case, at the end of the day, your standard library, as well as all the low-level syscalls, go down to WASI. And then from WASI is that layer, that sort of standardized layer that has different implementations on different hosts. So you have one for Windows and one for Linux and one for Mac, and maybe many actually on any given concrete platform, but you have at least one. And what this architecture allows us to do is weave our own implementation of WASI into that stack. And our implementation of WASI, ordinarily, the first time you run your program, is going to call out to the host version of WASI. But it's going to make one important distinction. It's going to take whatever request it gets from your app, and it's going to serialize it in some sort of redundant, fault-tolerant data store, could be Redis cluster, could be S3, could be Cassandra, could be whatever. And then when the host environment returns some sort of response, it's going to take that And it's also going to send it and serialize it in the fault-tolerant data store. In effect, all of the low-level system calls in your WebAssembly application are being written out in this stream of events. And these individual events describe all of the external interactions that are happening with your program. And what that allows us to do is, thanks to the deterministic nature of the WebAssembly VM, if something happens, we can actually reconstruct the running state of your application from basically a fold on all those events from the beginning of time to the last one before the failure event occurred. So this gives us the ability, this gives Golem the ability to provide transparent fault tolerance, which means if there's a fault in hardware or software or whatever, your program continues to survive that. Transparent update tolerance, which means you can push as many new versions and they don't interfere with currently running versions. And then flaky tolerance, which means that your system can interact with, if your system does interact with other components that are flaky, you don't see that because retry policies are automatically applied. And what this allows you to do is build code that looks impossibly simple, but is extraordinarily reliable. And this new approach to high reliability, it basically lets us kill off event sourcing. Right? There's probably hundreds of millions, maybe billions of lines of code out there that has been written to support and maintain these large-scale event source systems. And it should all go away. There's no reason we should ever have to be writing event source systems. It's not an easy thing to do. It's very complicated. You have to have a lot of knowledge to build and maintain these systems, and we don't need it anymore. But another super interesting thing that Golem gives us that we're still in the early stages of exploring is the fact that if your running program can't go down for any reason, then you can start storing important things in memory. Right? In this simple example, you can see we're using an in-memory list to hold the contents of the user's shopping cart. There's no need to store that in Redis or Postgres or DynamoDB. Why? Why would we do that? Our program can't go down. It's always going to be running. So memory becomes as reliable as a database, which means you can't literally delete databases, okay? Because we use databases for lots of reasons. But Golem lets you rethink the decision to use a database and a cache and a NoSQL store, and all the other decisions that we make instinctually in this age of stateless apps. We build stateless apps because we don't want to head down the path of event sourcing. But in the world of Golem, we can embrace state, and we can build stateful apps, and we can rely on that state to survive any sort of catastrophe at the level of the server or the hardware or whatever. We can treat memory as if memory itself is a database. Another very interesting thing, I think, is the relationship between Kubernetes and Golem. If you look at all the features that a framework, an orchestration framework like Kubernetes gives us, I mean, they're really great. We get automatic scaling and container management and just on and on and on. And Kubernetes has really given us like an operating system for distributed applications that lets us scale and monitor, provision, and manage our distributed applications. But a lot of these things are actually already being done by Golem itself at a different level of scale than Kubernetes was ever designed to handle. On Kubernetes, you can have, I think, around 200 or so pods per machine. The equivalent concept in Golem would be a running Wasm instance, and you can have hundreds of thousands of those dedicated to a machine. And they can all be stateful, and you can address any one from any other Wasm instance in the cluster. So even though this is not a short-term alignment, I think over the course of the next 2 to 5 years, you're going to see more and more alignment between the features that Golem has and supports and the features that Kubernetes has been giving us in a slightly different context, where instead of managing containers, Golem is helping you manage WebAssembly instances, with the ultimate goal being at some point, Golem provides a unified fabric for deploying, scaling, and operating all of your Wasm components with software-defined reliability. What does that mean? It means for some of your components, you don't really care if it's highly reliable, so you shouldn't have to pay the cost of that. And for others, like the checkout example, you really do care if that's reliable. So you turn up the knobs on reliability to the max. Right? Reliability should be something that we decide independent from the code. We should have knobs and switches that we use to tweak reliability up and down based on how valuable it is to us and how much we want to pay for that. And in that future, Golem provides that unified fabric that lets us deploy all of our workloads, even if those workloads contain mixed requirements for reliability. And then finally, Golem, because it embraces the WebAssembly component model, and because the component model allows you to say this component exports these types and these functions and these resources. And this is how component linking works, right? You compose components, and it works using these exported types, functions, and resources. Because Golem has embraced the component model 100%, it's gone all in on the component model, what this allows it to do is provide a way for your running WebAssembly instances to talk to other instances through the component model. Right? In a pure Golem cluster, you don't need gRPC. You don't need protobuf. You don't need JSON between your WebAssembly microservices. You don't need HTTP. You don't need any of that stuff. Why? Because you already have the component model, and the component model already has WIT. And WIT could be thought of as a better version of protobuf that's specialized to WebAssembly data type, well, WebAssembly component model data types. And so in the limit, Golem allows you to delete HTTP, JSON, gRPC, all the different formats out there. It's kind of silly to me that in 2024, we take our type data structures and then we figure out how to turn them into strings. And then we take those strings, well, byte arrays, and we send them over the wire. And then we figure out how to turn those strings back into type data structures. There's something wrong with that. And it's been wrong for a long time. I know we have things like protobuf that help us and do a great job. But fundamentally, in a world in which microservices are gone because the WebAssembly component model has killed them, and we assemble our applications from different components written in different languages, those components should be able to talk to each other whether they're locally composed and running in the same process or whether they're remote across network boundaries. And that's what Golem gives us, is the ability to take this great component model and extend it across time and space to do distributed computation. All right, so in summary, WebAssembly isn't just a toy. Right? This is serious, heavy-duty technology, and there's a better reason to use WebAssembly than it's the shiny new thing. Right? WebAssembly is enabling new classes of technology to exist that could not exist otherwise. You cannot build Golem on top of machine code. It cannot happen. You cannot build Golem for the JVM. It cannot happen. You can build Golem for WebAssembly. So WebAssembly is enabling us to build new types of things that have never before existed. And that's one of I think, many killer use cases for adopting WebAssembly. Number 3, Golem provides a highly reliable foundation for distributed apps. It's trying to allow us to write very simple code, very, very simple code that is extremely reliable. And previously, that combination was not possible. Right? You can have simple code, or you can have highly reliable code. You don't get to choose both of those. But Golem says you do get to choose both of them, thanks to this new thing called WebAssembly. And then finally, I hope you've seen by attending many of the great talks today that disruption in the cloud-native ecosystem is right around the corner. There's a lot of really exciting things happening. And the component model, Golem, Wasm Cloud, all the great stuff that's being done out there is going to change the way we build cloud-native applications. I hope you're all as excited about that as I am. All right, that's it. Thank you very much for attending my talk. I don't know if I have any time for questions. I hope I have time for one.
Hello, awesome presentation. So you talk about the determinism in Wasm is kind of one of the key pieces. I wonder if you have thought about how to handle multi-threading in this context.
It's not fun. It's not fun. And it's going to come down to exactly how Wasm ends up supporting multi-threading. But in a shared everything scenario, it's not great because you need to identify points where shared memory is read and points where shared memory is written to. And those become points that you need to create a record in the log, so that if you're restoring the state of that running process, you can restore it to exactly what it was, despite all the concurrency that's otherwise happening. So it's not a fun process. It is possible. And if Wasm threads ends up succeeding and being adopted, then we'll probably support it. But it's not going to be pretty. That's going to be some very ugly looking code, I think.
Awesome. Thank you.
Yeah.
Hello. So thank you very much for the presentation. It was really good. So I think that Wasm, in this sense, we're talking about reliability and trying to recreate the state that we had in the past before the disruption. I think about it about if you ever play video games on an emulator, have you played? You can do that already. I think it's a similar idea, right?
Yeah.
If I close my emulator, but I save the state of the game, then
Yes.
I can, because I guess that you are dumping memory of the heap
Yes.
and stack and all that. Okay. So if I understood correctly, you're synchronizing wherever a call to the WAS CDK is done. For example, if you're doing a system call. So that means that some sections of the code, imagine that you are assigning numbers, moving things around, but you're not calling any system call. It would mean that between those 2 points, there will be no synchronization. Am I right?
That's correct.
Okay.
And that lets you do a huge amount of CPU work, right, without any network, because that CPU work, if there is a failure event and you have to replay it, it's going to produce the same in-memory state as an outcome. So that means CPU-driven workloads are very, very efficient, because there's almost no synchronization points in that type of code.
Yeah, I was just wondering because I don't know if you're doing ahead of time compilation for those Wasm modules, because otherwise it would be even harder to control what happens between syscalls, right?
Yeah. Okay. Yeah, it minimizes network bandwidth. It adds a very tiny amount of network bandwidth to your running app. But for CPU work, there's no network I/O.
Okay, thank you very much.
Great question. It's all open source, so please check it out and give us feedback, report bugs, play around with it. It is not 1.0, so don't put your boss's application checkout API onto that system right now, because we'll probably be hearing from that. But July is our target date for a 1.0 that you can ship stuff on. Okay, thank you very much.